Hello friends, this is Jayant Ronkar working as a Assistant Professor in Department of Information Technology, Tulsi Ramji Gaikwad Patil College of Engineering and Technology. Friends, today we are going to learn about clock synchronization, and it is the basically topic of subject distributed system. So we will start with basic idea behind the clock synchronization. In any centralized system, time is unambiguous. When a process wants to know the time, it make a system calls and the kernel tell it. If process A asks for time and then little later process B asks for the time, the value of that B get will be higher than that of A, which is got by A. It will certainly not be the low. In distributed system, achieving agreement on time is not trivial. Just think for a moment about the implementation of lack of global time on a Unix make program as a single example of this. Normally in Unix, large programs are split into multiple sources of file so that change to one source file only require one file to be recompiled, not all the files. If a program consists of 100 files, not have to recompile everything because one file has been changed, greatly increase the speed of which programmer can run. So the way make normally works is simple. When a programmer has finished changing all the source file, he runs make, which examines the time at which all the source and input files or object files were last modified. If the source file, that is input.c, has time 2151 and corresponding object file, that is input.o, has time 2151, make knows that input.c has been changed since input.o has created, and thus input.c must have recompiled. On the other hand, if input.c has time 2144 and output.o has time 2145, no compilation is needed. Thus make goes through all the sources files to find out which one need to be recompiled and call the compiler to recompile them. Now imagine that what would happen in a distributed system in which there were no global agreement on time. Suppose that output.o has time 2144 as given above, and shortly thereafter output.c is modified, but his assigned time is 2143 because the clock is on its machine is slightly behind as shown in given figure, where in this figure it represents when each machine has its own clock, and event that occur after another event may nevertheless be assigned on earlier time. So in this figure it shows that at what time what event is going to happen. Make will not call the compiler. The resulting executable binary program will then contain a mixture of object files and the old sources and the new sources. It will probably crash and the programmer will go crazy trying to understand what is wrong with the code. So there are many more examples where the accurate account of time is needed. The example above can easily be reformulated to a file timestamp in general. In addition, think of application domains such as financial knowledge, security auditing, and collaborative sensing, and it will become clear that accurate timing is required whenever the machines or whenever the nodes are communicating with the processes. So since the time is the basic to the way people think, and effect not having the clock synchronization can be dramatic. If fitting that to begin our study of synchronization with the simple question, is it possible to synchronize all the clocks in distributed system? So the answer is surprisingly complicated, because can we do the synchronization with all the clocks available on all the machines or not? That is what the complicated question. So now we will see how we will learn about the physical clock. In this, nearly all the computers have a circuit for keeping track of time. Despite widespread use of the word clock to refer to this device, they are not actually clock in the usual sense. Timer is perhaps a better word. A computer timer is usually prescribed machine quartz crystal. When kept under the tension, quartz crystal oscillate at a well-defined frequency and depend on the kind of crystal, how it is cut, and the amount of tension associated with each crystal are two registers, a counter and holding register. Each oscillation of the crystal decrement the counter by 1. When the counter get 0, an interrupt is generated and the counter is reloaded from the holding register. In this way, it is possible to program a timer to generate an interrupt 60 times a second or at any other desired frequency. Each interrupt is called one clock tick. When the system is booted, it is usually asked the user to enter the date and time, which is then converted into the number of ticks after some known starting date and it is stored in the memory. Most computers have a special battery backup CMOS RAM. So most of the computers are having the battery backup CMOS ROM on which the date and the time need not be entered on subsequent boots. So at every clock and every clock tick, the interrupt service procedure add 1 to time stored in memory. In this way, the software clock is kept up to date. With a single computer and a single clock, it does not matter much if this clock is off by a small amount or it is off by any of the amount. Since all the processes on the machine use the same clock, they will still internally consistent. For example, if file input.c has time 2151 and file input.o has time 2150, make will recompile the source file even if the clock is off by 2 and the two time are 2153 and 2152 respectively. And that really matters, the relative terms. So as soon as the multiple CPU are introduced, each with its own clock, the situation change radically. Although the frequency at which the crystal oscillates run is usually fairly stable, it is impossible to guarantee that the crystal is different computer all run at exactly the same frequency. In practice, when a crystal has n computer, all n crystal will run at slightly different rates, causing the software clock gradually to get out the synchronization and give the different values when it read out. Thus, the difference in the time value is called a clock skew. As the consequences of this clock skew, the program that expect the time associated with the file, object, process or the messages to be correct and independent of the machine on which it is or it was generated. So this is about the basics of clock synchronization, and in this physical clock synchronization, this figure shows that the computation of mean solar day. Here in this diagram, the sun is at the center of this diagram and around the orbit of the earth it is shows the clock in each and every machine. So in this diagram the digress slightly to see how the time this diagram shows how time is actually measured. It is not really as easy as might think, especially when high accuracy is required since the invention of mechanical clock in the 17th century. The time has been measured astronomically. Every day the sun appears to rise on the eastern horizon, then climbs on the maximum height in the sky and finally sink in the west. The event of that sun's reaching to the highest apparent point in the sky is called a transit of the sun. These events occur at about noon each day. This interval between two consecutive transit of the sun is called a solar day. It is called a solar day. Since there are 24 hours in a day, each containing 3600 seconds, the solar second is fixed as exactly 1186400th of the solar day. The geometry of mean solar day calculations are given in this diagram. In 1940, it was established that the period of the Earth rotation is not constant. The Earth orbit is slowing down due to tidal friction and atmospheric drag. So, based on the studies of the growth of patterns in ancient coral, geologists now believe that 300 million years ago there were about 400 days per year. The length of the year is not thought to have changed. The day has simply become longer. In addition to this long-term trend, short-term trend and short-term variations to the length of the day also occurs, probably causes the turbulence deep in the Earth's core of molten iron. So this revolution led astronomer to compute the length of the day by measuring the large amount of or large number of day and taking the average before the dividing 86400. The resulting quartz was called the mean solar seconds. So this is what the physical clock, and accordingly we have to calculate the clock accordingly. Then we will see the global positioning in the clock synchronization. Here in global positioning system, as the step toward the actual organization of the synchronization of the problem, we first consider the related problem, namely determining one's geographical position where on the earth. The positioning problem by itself solved by highly specific dedicated distributed system, namely GPS, which is acronym to the global positioning system. GPS is a satellite based distributed system that was launched in 1978. Although it has been used mainly for military applications, in recent years it has been found in the way to many civilian applications, notably for traffic navigation. However, many more applications domain exist to use this GPS. For example, GPS phones now allow to let callers track each other's positions, a feature which may show to be extremely handy when you are lost or in trouble. This principle can be easily applied to tracking other things as well. including the pets, children's, cars, boats, and so on. So GPS very useful to track all the things. So in this diagram, computing a position in two-dimensional space is given. Here in this diagram, it represents, in order to compute a position, consider first two-dimensional case as shown in this figure, in which two satellites are shown and drawn along the circle, representing points at the same distance from each respective satellite, and the y-axis represent the length, while the x-axis represent the straight line, and it represents a straight line along the Earth's surface at a sea level. So ignoring the height point, we see that intersection of two circle is unique point. So this principle of intersecting circle can be expanded to three dimension, meaning that we need these three satellites to determine the longitude, latitude, and attitude of the receivers on the earth. This positioning is all fairly straightforward, but matters become complicated when we can no longer assume that the clock as per perfectly synchronized. So there are two main important real world facts that we need to be considered into account. First one is, it takes a while before data on a satellite positions reaches to the receiver, and second one is, the receiver clock is generally not to be synced with that of the satellite. So this is what the global positioning system work to give you the time, and accordingly you can search the locations. You can search anything by using the global positioning system. So this is what about the clock synchronization and global positioning system. So thank you.